Welcome back to the Deep Dive. Today, we are wading into, well, what might be the most complex, paradoxical, and frankly high-stakes battlefield in the entire human body.
It really is. It's a system where the difference between, survival and death is often a matter of molecular negotiation.
Negotiation, that's an interesting word for it. We're talking about immunity and inflammation, and we're looking at it through the lens of Pharma 34, Defense with Consequences. Now, that title, it feels a bit ominous. Consequences usually implies something went wrong.
Or that the right thing has a cost. Look, the immune system it's unique in physiology.
How so?
Well, think about other systems. The heart pumps, the kidneys filter. The immune system is the only system in your body that is explicitly designed to kill.
Right. Its whole job is to destroy things.
To identify biological entities and just destroy them. And usually that means invaders, bacteria, viruses, fungi.
But then the gun's on the host.
That's the classic autoimmune scenario, sure. But the consequence is even more subtle than that. I mean, in our attempt to pharmacologically stop it from shooting the host, we disarm it so completely that the real invaders just walk right in.
It's the double-edged sword.
In the truest sense.
Yeah.
If you blunt the blade to save yourself, you can't use it on the enemy.
So to help us navigate this mess, we are pulling from our two heavyweights. We've got the clinical clarity of Katzun, specifically their chapter on immunopharmacology, and we're blending that with the just heavy molecular depth of Goodman and Gilman's chapter on immunity and inflammation.
And you really need both. Think of Katzun as the field manual.
Okay.
It tells you what drugs we use, when we use them, what are the clinical tables telling us. Goodman and Gilman is the blueprint of the machinery.
It's the how.
It's the how the gears turn at the cellular level. And trust me, you can't prescribe the drug if you don't understand the gear it's designed to jam.
Before we get lost in the alphabet soup of cytokines and receptors, I want to anchor this whole discussion. Katzun presents a case study that I found, frankly, terrifying.
Ah, yes.
I want to keep coming back to this patient because she really represents everything we're talking about.
The 59-year-old woman with myelodysplastic syndrome.
Right, let's call her Mrs. G. So her bone marrow is failing. It's just pumping out garbage cells. So the doctors decide she needs a total reset.
A scorched earth policy.
Exactly. They give her high-dose chemotherapy to wipe her marrow clean, and then they give her a stem cell transplant from a donor.
An allogeneic transplant. And this detail is critical. She isn't just getting new cells.
She's getting a whole new immune system.
A completely new immune system. Her body's genetic code is one thing. Her immune system's genetic code is now from someone else entirely.
And at first, she seems to be doing okay. She's on prophylactic drugs, tacrolimus and methotrexate. But a month later, it all falls apart. She gets a rash. Then, just voluminous bloody diarrhea. The diagnosis is grade the 4th order acute graft versus host disease, GVHD.
This is the nightmare scenario. Her new immune system, the graft, has woken up. It's looked around at Miss G's skin and her gut, the host, and it has said, "You are not me. You are the enemy."
And it launches a full-scale war.
A war to destroy her from the inside out.
So the doctors do the only thing they can. They hit her with high-dose prednisone, then methylprednisolone. Just massive immunosuppression.
Right.
And this is the tension I just can't wrap my head around. We are nuking her immune system right when she's trying to recover from chemotherapy, which she's at her most vulnerable.
That is the central paradox. It's the balancing act. To save her from her own new immune system, we have to suppress her defenses. But in doing that, we leave the castle gates wide open to every infection imaginable.
Fungal pneumonia, CMV, sepsis.
Everything. Every single pharmacological decision here is a gamble. We're trying to stop this very specific attack without causing a total security collapse.
That's a terrifying balance to strike. Okay, so to understand how we even begin to intervene in this war, we need to map the battlefield.
We do, and that map starts by distinguishing the two main armies we have. There's the innate immune system and the adaptive immune system.
I've heard these described as the local police versus the SWAT team. Is that too basic for Goodman and Gilman?
It's a decent starting point, but we can deepen it. The innate system. It's not just the police. It's the castle walls, the moat, the automated turret guns.
The first line of defense.
And it's ancient, evolutionarily ancient. It's incredibly fast. We're talking minutes to hours, and it relies on hardwired recognition. It doesn't learn, it just reacts.
Okay, and the adaptive system.
That's the sniper unit. It takes days, sometimes weeks to mobilize.
Why so long?
Because it has to custom build its weapons for a very specific enemy,
Yeah.
but once it builds them, it never ever forgets. That's memory.
All right, let's start with the innate side then, the castle walls. Katzung emphasizes this concept of self versus non-self. But before any cells even get involved, there are the barriers.
Right. And they're not passive at all.
I was surprised by just how aggressive our passive barriers are.
Oh, absolutely. I mean, take your skin. It's not just a wrapper. The epidermis is a physical shield, sure, but it's also a chemical warfare zone.
How so?
Your skin actively secretes antimicrobial peptides called defensins,
Defensiveness.
little proteins that literally punch holes in bacterial membranes. And then think about your stomach.
The acid.
A pH of 2. It's hydrochloric acid. It dissolves almost everything you swallow. Even your tears have lysozyme, an enzyme that it cleaves the cell wall of bacteria.
So we're constantly bathing ourselves in disinfectant.
Constantly. Infection usually only happens when these barriers are physically breached.
Okay, so let's say a barrier is breached. Let's go back to Mrs. G. She has a central line in her chest for the chemo. That is a breach. A bacteria gets in.
Yep.
How does the body know? Instantly. You said the innate system is fast. Does it just see the bacteria?
Not with eyes, no. It uses pattern recognition. And this is where Goodwin and Gilman gets really interesting. Human cells look a certain way. Bacteria, on the other hand, look fundamentally different.
How?
They have structural components that we just don't have. We call these PAMPs.
AMPs.
Pathogen-associated molecular patterns.
So it's like a barcode on the bacteria that says, I don't belong here.
Exactly like a barcode. The most famous one is lipopolysaccharide, or LPS. It's a major part of the outer wall of gram-negative bacteria. Or double-stranded RNA.
Right, because our RNA is usually single-stranded.
Most of the time, yes. So if a cell sees double-stranded RNA floating around, it's a pretty safe met it's a virus.
So our immune cells have barcode scanners for these things.
They do. They're called PRRs, pattern recognition receptors. And the most critical family of these are the toll-like receptors, or TLRs.
I've heard of these. Why are they called toll? Is that like a toll booth?
It's actually a funny story. It comes from a German researcher who found them in fruit flies. She looked under the microscope and apparently shouted, "Das ist ja toll," which means, that is amazing.
Huh. Okay. So in humans, they're important.
They are vital, and Goodman and Gilman really highlights one in particular, TLR4.
And what does TLR4 do?
It's the specific scanner for LPS. So imagine a macrophage, one of our innate immune cells, just sitting in Mrs. G's tissue. A bacterium floats by. The LPS on that bacterium slots right into the TLR4 receptor on the macrophage.
Like a key in a lock.
A key in a lock, and that turns the key.
And what happens when the key turns?
It triggers this massive signaling cascade inside the cell. I mean, we should talk about this pathway, because a lot of drugs target it. TLR4 recruits a protein called MyD88. This kicks off a whole chain reaction.
A phosphorylation chain.
Right, which eventually wakes up a transcription factor called NF-kappa.
NF-kappa. I see that name highlighted everywhere in the notes. It seems important.
It's the master switch. It is the master switch for inflammation. Normally, NF-kappa B just sits quietly in the cytoplasm, sort of held prisoner by an inhibitor protein.
Okay.
The TLR signal sets it free. It marches into the nucleus, it binds to the DNA, and it turns on the genes for war.
War meaning?
Cytokines, the alarm sirens. The macrophage starts screaming chemically to the rest of the body, "We have a breach!" It starts pumping out things like IL-1, IL-6, and TNF-alpha.
So the key here is speed. The innate system doesn't need to know which specific bacteria it is.
Nope.
Just that it is a bacteria and not one of us.
Precisely. But there's another weapon in the innate arsenal that's even faster than the macrophage. It doesn't even require a cell. It's just already in the blood, waiting.
The complement system.
The complement system.
This part of the reading always confuses me. It feels like this incredibly complicated Rube Goldberg machine. You know, C1 hits C2, which hits C4. Why is it so complex?
Because it's dangerous. Think of complement as a series of hand grenades just circulating in your blood. You want the pin to be very, very secure until the absolute moment you need to pull it. The complexity is a safety feature.
So what pulls the pin?
Well, there are 3 different pathways that can, but let's focus on the result. The cascade converges on one central event, splitting a protein called C3. This releases a fragment called C3b.
And what does C3b do?
Katzung describes 3 main consequences. First is opsonization.
Opsonization.
C3b is sticky. It just plasters itself all over the surface of the bacteria. I call this buttering the toast.
Because it makes the bacteria tastier for the immune cells.
It makes them grippy. Phagocytes, the eater cells, have a hard time grabbing onto slippery bacteria. but they have receptors for C3b. So if a bacterium is coated in C3b, the phagocyte can just grab it and devour it instantly.
Okay, so buttering the toast. What's the second thing?
Chemotaxis. The other fragments that break off, C3a and C5a, they float away, and they act like a scent trail.
A come here signal.
Exactly. They drift downstream and basically tell other immune cells like neutrophils, hey, follow the smell, the fight's over here.
And the third one. This is the one that sounds like science fiction.
Lysis. It's called the membrane attack complex, or MAC.
NAC.
The final components, C5b all the way through C9, they come together and they literally self-assemble into a tube, a hollow tube, and they punch a physical hole through the bacterial cell wall.
So they're drilling into the enemy ship.
They drill thousands of holes, water rushes in, all the salts rush out, and the bacterium it explodes. It's brutal and incredibly effective.
But wait, if we have proteins circulating in our blood that can build drills and punch holes in cell membranes, what stops them from punching holes in our cells?
That is the consequence question, right? We have regulatory proteins on our own cells. They're like little signs that say, don't drill here. They deactivate the complement proteins when they land on our cells.
But sometimes those signs are missing.
Sometimes those regulators are missing. This is what happens in a rare disease called PNH, paroxysmal nocturnal hemoglobinuria.
Right, I remember reading about that.
In PNH, the patient's red blood cells are missing that don't drill me sign, specifically proteins called CD55 and CD59. So the complement system sees a red blood cell, assumes it's a valid target, and just drills holes in it. The patient lyses their own blood.
That sounds horrific. So how do we stop a system that's just, free-floating in the blood?
We use a drug, a monoclonal antibody called eculizumab. It works by binding to the C5 protein.
So it stops the drill from ever being built in the first place.
It basically puts a safety lock on that final grenade. It stops the membrane attack complex from forming. It's great for saving the red blood cells in PNH, but
Here comes the trade-off.
The membrane attack complex is our absolute main defense against a specific bacteria called Neisseria meningitis,
Meningitis.
the one that causes bacterial meningitis. So if you put a patient on eculizumab, you have effectively turned off their primary defense against that one bug.
So you cure their anemia, but you might kill them with a brain infection.
That's why every patient on eculizumab needs to be vaccinated and watched like a hawk. You fix one very serious problem, but you create a new, very specific vulnerability. Defense with consequences.
Okay, so let's move from recognition to the actual battle. Inflammation. Goodman and Gilman quotes the ancient Roman definition. Rubor, tumor, calor, dolor.
Redness, swelling, heat, and pain.
Right. And I always thought of these as just annoying symptoms, things to be treated with ibuprofen. But the text argues they're actually functional tactics.
They are absolutely tactical. I mean, think about the logistics of war. You have an infection in your finger. Your best soldiers, the immune cells, are in the blood, zipping by at high speed.
In the highway of the circulatory system.
Exactly. You need to get them off the highway and into the side streets of the finger tissue.
So the redness and the heat, that's the first step.
That's vasodilation. The blood vessels widen. This does two things. It slows the blood flow down, like a river widening into a lake, and it brings more blood, and therefore more soldiers, to the area. That's your rubor and calor.
And the swelling. The tumor.
That's permeability. The endothelial cells that line the blood vessel, they actually pull apart slightly. They create little gaps. This allows fluid and proteins, like that complement system we just talked about, to leak out into the tissue.
But the real magic trick is getting the cells out. Goodman and Gilman calls it diapedesis, or extravasation.
And this is a biomechanical marvel. It's not that the cells just leak out. It's a very elegant four-step process.
Okay, let's break it down, because this is where a lot of the modern drugs work. Step 1.
Rolling. The white blood cell, the leukocyte, is flying down the vessel. The inflamed vessel wall starts to put up these little speed bumps or hooks called selectins.
Okay.
The leukocyte bumps into them. It doesn't stop, but it starts to tumble and roll along the edge of the vessel. Think of it like Velcro that's not quite stuck. It catches and releases, catches and releases. It slows the cell way down.
Okay, so it's rolling. Step 2.
Activation. As it's rolling, the leukocyte detects chemical signals, chemokines like IL-8, that are seeping out from the infected tissue. This signal is crucial. It tells the cell to change the shape of proteins on its own surface, called integrins.
It changes their shape.
Yes, and this is a key molecular detail. The integrins normally sit in a low-affinity bent state. They're not very sticky. When the chemokine signal hits, they snap open into a high-affinity state. They become super stiff.
It leads to step 3.
Adhesion. sticking the landing. The now activated sticky integrin, specifically one called VLA4 locks, onto a receptor on the vessel wall called VKM1. This isn't a tumble anymore. This is a dead stop. The cell just flattens out against the wall.
And finally,
Transmigration. It finds a gap between those endothelial cells and it squeezes through, crawling out of the blood vessel and into the tissue to find the fight.
now the reason we care so much about this molecular dance is because in diseases like MS or Crohn's, this is the exact process that's happening where it shouldn't be.
Exactly. In multiple sclerosis, T cells are performing this dance to get into the brain and attack the myelin. In Crohn's disease, they're using it to get into the gut wall.
So if we can somehow lock the door,
You can stop the disease. Enter natalizumab. It's a monoclonal antibody that is designed to stick to that alpha-4 integrin.
the sticky molecule on the white blood cell.
Right. If you block the alpha-4, the cell can still roll, but it can never perform that crucial adhesion step. It can't stick. It just keeps rolling and floats right past the brain or the gut. It's incredibly effective for MS.
Does it block entry everywhere? I mean, if I'm on natalizumab for my MS and I get a gut infection, can my immune cells get to my gut to fight it?
That's the problem. With natalizumab, you're blocking that VLA4 integrin everywhere. So yes, you are blocking gut entry too. But pharmacology is always about precision.
So we got more specific.
We developed a second drug, vedolizumab. It targets a very specific combination, the alpha-4 beta-7 integrin.
That sounds like a coordinate.
It's basically a zip code. The alpha-4 beta-7 integrin is the specific passkey used to enter the gut mucosal tissue. It is not the main one used to enter the brain.
Wow.
So vedolizumab can block inflammation in the gut for diseases like ulcerative colitis or Crohn's, but it leaves the immune surveillance of the brain perfectly intact.
That is just wild. We are essentially hacking the GPS system of our immune cells.
That's a perfect way to put it. But let's go back to Mrs. G. Her T cells are attacking her gut. In theory, vedolizumab could help her by stopping more T cells from getting into the gut. But the problem is
The T cells are already there.
the killers are already inside the house.
Yeah.
Which brings us to the generals of this war, the adaptive immune system, the T cells and B cells.
The snipers.
Right. The innate system holds the line, but the adaptive system is what clears the infection for good, or, in Mrs. G's case, clears the host.
So Kinzong talks about antigen presentation. We use the hot dog bun analogy in the outline, but why is this process so tightly controlled? Why can't a T cell just see a virus the way a macrophage does with its TLRs?
Because T cells are, for all intents and purposes, nuclear weapons. You cannot have them detonating on a hunch. They require something called MHC restriction.
MHC restriction.
The T cell receptor, the TCR, is designed to only recognize an antigen if it is presented on a very specific silver platter, the MHC molecule. It won't recognize a free-floating virus particle. It has to be processed and shown to it by a professional.
A professional being a dendritic cell or a macrophage.
Exactly, an antigen-presenting cell, or APC, and this is where the famous two-signal hypothesis comes in. This was a huge concept in the reading.
Right. It's the feel-safe.
It is the ultimate failsafe. Signal 1 is the recognition part. The T cell receptor binds to the MHC plus antigen complex that basically says, I see the enemy.
But that's not enough to fire the weapon.
No. In fact, if a T cell only gets signal 1, it actually shuts down permanently. It becomes anergic. To activate, it needs a second distinct signal.
Signal 2.
Signal 2, co-stimulation. A molecule on the dendritic cell, usually CD80 or CD86, must physically plug into a receptor on the T cell called CD28.
So signal 1 is this is the target, and signal 2 is you have permission to kill it.
That's it exactly. And this two-key system is a major drug target. Take rheumatoid arthritis. You have T cells that are wrongly attacking the joints. We want to stop them.
So we use a drug called abatacept.
Right. And what abatacept does is it acts as a decoy. It's a protein that's designed to look like the CD28 receptor. It floats around and binds up all the CD80 and CD86 on the antigen-presenting cells.
So it steals signal 2.
It completely removes the permission to kill. The T cell sees the joint tissue, that's signal 1, but it never, ever gets signal 2. So it doesn't attack, it just goes to sleep.
That's so clever. But okay, let's say a T cell is properly activated, both signals. It doesn't just stay a generic soldier. It specializes.
It does. This is the Th1, Th2, Th17 paradigm from Goodman and Gilman. Depending on the cytokine environment at the very moment of its activation, a helper T cell, a CD4 cell, chooses a career path.
Let's run through them, because different diseases seem to map onto these different subsets.
Okay, so first you have the Th1 cells. These are driven by a cytokine called IL-12. Their job is to produce interferon gamma, and that tells macrophages to get really, really good at killing things that are hiding inside our own cells.
Like tuberculosis or certain viruses.
Exactly. They're the intracellular specialists. Then you have Th2 cells.
Okay.
These are driven by IL-4. Their main job is to fight parasites like worms. But in the developed world, where we don't have many worms, they're mostly responsible for allergies and asthma. They help B cells make IgE antibody.
The allergy antibody.
Yeah.
And then Th17. These sound nasty.
They are the riot police. They get recruited by IL-23, and they spit out a cytokine called IL-17. And what IL-17 does is recruit massive, massive numbers of neutrophils to a site. These are the main bad guys in diseases like psoriasis and inflammatory bowel disease.
And finally, there's a fourth type. The TREGs.
The regulatory T cells, they are the peacekeepers. They express a transcription factor called FOXP3. Their entire job is to shut the other three types down and prevent autoimmunity, to maintain tolerance.
I want to touch on one more T-cell concept that has just exploded in cancer therapy in the last decade. Checkpoint inhibition.
Ah, yes.
The brakes.
So normally a T cell has a built-in off switch, a timer.
It has to. After fighting for a while, a T-cell starts to express new receptors on its surface, like PD-1 or CTL4. If these receptors get triggered, the T-cell stops attacking. It's a safety mechanism to prevent the T-cell from destroying the very tissue it's trying to save from infection.
But cancer is clever. It hacks the system.
Cancer is evolution in hyperspeed. Tumors learned that if they express the ligand for PD-1, a molecule called PD-L1, they can trick the T-cells. The tumor cell reaches out, it high-fives the PD-1 on the attacking T-cell, and it basically says, hey, I'm one of you. Relax. Go to sleep. The T-cell gets the off signal, it turns off, and the tumor grows completely unharmed.
So the drugs pembrolizumab, which is Keytruda, and nivolumab.
They are checkpoint inhibitors. They are antibodies that physically block that interaction. They sit on the PD-1 receptor so the tumor can't press it. They put a piece of tape over the off button, so the T-cell just... It can't be turned off. It just keeps killing the cancer.
Which has been a miracle for melanoma and lung cancer and many others. But let's go back to our theme, consequences.
If you take the brakes off the immune system,
It doesn't just attack the cancer anymore. It starts to attack everything. And we see this whole new class of side effects called immune-related adverse events.
like what?
Colitis, pneumonitis, thyroiditis, hepatitis, any atophytis you can think of. We are essentially inducing a temporary and sometimes permanent autoimmune disease in order to cure the cancer.
It seems like you can never just do one thing. Every intervention just ripples out. Which leads us perfectly into section 4. When the defense itself becomes the disease, Katzon talks about hypersensitivity and autoimmunity.
Let's focus on type 1 hypersensitivity, what we call allergy, because there's a concept here that's really important for drug safety, the hapten concept.
This is what explains why some people are allergic to a drug like penicillin.
It's exactly why. Penicillin, by itself, is a tiny little molecule. It's too small for an immune cell to see it or present it on an MHC bun. It should be immunologically invisible.
So why does it cause anaphylaxis?
Because penicillin is chemically reactive. It has a beta-lactam ring that can pop open and covalently bind to proteins in your blood like albumin.
Okay.
So now you don't have penicillin and albumin, you have a new big thing, an albumin-penicillin complex. The immune system looks at this and says, wait a minute, that albumin looks weird, it's been modified, it's not self anymore, attack it.
So you aren't allergic to the drug. You're allergic to your own proteins that have been vandalized by the drug.
That's the perfect description. The first time you take it, your body gets sensitized. You make IgE antibodies against this new complex, and those IgE antibodies go and sit on mast cells or tissue-based grenades. You feel fine.
But the second time,
The second time you take the drug, it enters your system, it binds to the albumin again, and that complex immediately cross-links all the IgE sitting on your mast cells. Boom! Degranulation. Massive amounts of histamine flood the system. Your blood vessels dilate. Your blood pressure plummets. Your airways constrict. That's anaphylactic shock.
now Katzon mentions this procedure called desensitization. This sounds absolutely insane to me.
Mm-hmm.
If someone is deathly allergic to penicillin, but they need it for, say, neurosyphilis,
Yeah.
we just give it to them anyway.
Very, very, very slowly. In an ICU, we start with a microdose, something that's a millionth of the final dose.
And what does that do?
It triggers the mast cells just a tiny bit.
Really?
A little histamine leaks out. Then we give a slightly bigger dose, PFT. We are trying to empty the grenades slowly, molecule by molecule, so they never reach the threshold to explode all at once.
That sounds like diffusing a bomb by tapping it gently with a hammer.
It is extremely high risk, and it's temporary. As soon as the drug is cleared from the patient's system, the mast cells refill with histamine and IgE, and the patient is fully allergic again.
Let's pivot to autoimmunity. We know the basic mechanism tolerance fails, the immune system attacks self. But Goodman and Gilman makes a really important point about the long-term damage. It's not just the active inflammation that destroys organs. It's the healing process itself.
Fibrosis. This is the silent killer in so many chronic diseases. Chronic inflammation is a constant signal for repair. It triggers cells called fibroblasts to lay down collagen, to build scar tissue.
So if you have chronic inflammation in the lungs, like an idiopathic pulmonary fibrosis, or in the liver from chronic hepatitis,
Your normal functional tissue gets replaced, bit by bit, with useless scar tissue. And scar tissue doesn't do the job.
scar tissue in the lung doesn't exchange oxygen.
And scar tissue in the liver doesn't filter toxins. This is why we treat diseases like RA or lupus so aggressively now. We aren't just treating today's pain, we're trying to prevent next year's fibrosis. Because once that tissue is scarred, it's gone for good.
Which brings us, finally, to the arsenal. Section 5. We've mapped the enemy, we know the terrain. Now, what weapons do we have? And more importantly, what are they using on poor Mrs. G?
We can classify these drugs into 3 broad categories. There's the sledgehammer, which is the corticosteroids. Then there are the sniper rifles, the biologics. And then the small molecules, which are sort of in between.
Let's start with the sledgehammer. Glucocorticoids. Prednisone. Mrs. G is on high doses. How does it actually work? I know it reduces inflammation, but mechanistically, what is it doing?
It works at the genetic level. Steroids are lipids, so they slide right through the cell membrane. Inside, they bind to a receptor in the cytoplasm, and that whole complex moves into the nucleus.
Okay.
In the nucleus, it binds to specific sequences on the DNA called glucocorticoid response elements.
And what does it tell the DNA to do?
2 main things. First, it turns on the genes for anti-inflammatory proteins, like I-kappa B, which is the protein that holds our friend NF-kappa B prisoner.
So it reinforces the jail cell for the master switch.
Exactly. And second, and maybe more importantly, it directly turns off the genes for almost every single inflammatory cytokine you can think of. IL-1, IL-2, IL-6, TNF. It essentially tapes the pages of the war cookbook together so the cell can't read them.
That sounds incredibly comprehensive.
It is. It's also lympholytic. High doses of steroids actually kill lymphocytes. They cause lymph nodes to shrink. It's why we use them as chemotherapy for leukemia and lymphoma.
But the side effects, Mrs. G is going to feel this.
Oh, she will. Metabolically, she'll develop hyperglycemia, steroid-induced diabetes. Her bones will start to thin out. That's osteoporosis. Her skin will become fragile. Mentally, she could experience psychosis or depression. And of course, on top of all that, she is profoundly immunocompromised.
So steroids are powerful, but they are messy. Let's talk about the small molecules. Before her GVHD got bad, Mrs. G was on tacrolimus and methotrexate for prophylaxis. Why those two?
Tacrolimus is a calcineurin inhibitor. This is pure signal transduction interference. Remember how we said T cells need 2 signals to get activated and grow?
Right.
Well, when a T cell is stimulated, calcium rushes into the cell. That calcium binds to a protein called calmodulin, and that complex activates an enzyme called calcineurin.
Calcineurin.
Calcineurin is a phosphatase. Its job is to clip a phosphate off of a transcription factor called NFAT.
Okay, that's a lot of acronyms. What does NFA do?
When NFAT is dephosphorylated, it goes to the nucleus and it tells the T cell to make IL-2. And IL-2 is basically T cell food. It's the primary growth factor that tells T cells to divide.
So let me see if I have this. Tacrolimus blocks calcineurin, which means NFAT never gets activated,
Right.
which means no IL-2 is made, which means the T cells starve and can't proliferate.
Exactly. They starve. Cyclosporine works the same way. This is the cornerstone of modern organ transplant medicine. You starve the attacking T cells of their growth signal.
But tacrolimus is famous for being hard on the kidneys.
Yes, nephrotoxicity is the major dose-limiting side effect. Plus, it causes hypertension and tremors. It has what we call a narrow therapeutic index. The difference between the dose that works and the dose that poisons you is razor thin.
In methotrexate.
That's more of a classic cytotoxic agent. It's an older drug. It inhibits an enzyme called DHFR, dihydrofolate reductase. Basically, it stops cells from making new DNA bases.
So if you can't make new DNA, you can't divide.
They can't divide. And since immune cells need to divide incredibly rapidly to mount an attack, methotrexate hits them very hard. But of course, it also hits the lining of your gut, your hair follicles, anything that divides fast.
Finally, let's talk about the modern era, the biologics, the sniper rifles.
These are the monoclonal antibodies. They all end in aramab.
Right.
And unlike steroids, which hit 100 different genes, these are designed to hit one specific protein.
And the biggest class by far is the TNF-alpha inhibitors, drugs like infliximab, adalimumab humira.
These drugs change the world for patients with rheumatoid arthritis and Crohn's disease. TNF-alpha is arguably the master cytokine of inflammation. If you can neutralize it, the whole inflammatory cascade can collapse. Patients often feel better in days.
But I know there's a but coming.
Tuberculosis.
TB, what's the connection?
Here's the thing about TB. In many people, your body can't actually kill it and eradicate it, so what it does is it walls it off. Macrophages surround the bacteria and build a prison made of cells called a granuloma.
Okay.
And it turns out that TNF-alpha is the structural engineer that keeps that prison wall intact. TNF-alpha is the warden.
So if Mrs. G had a latent TB infection from 20 years ago that she doesn't even know about, and we give her a TNF-alpha inhibitor,
The warden gets fired, the prison walls dissolve, the TB bacteria wake up, escape, and disseminate throughout the body. This is why you must screen every single patient for latent TB before starting one of these drugs.
let's hit a few others quickly. IL-17 inhibitors, like secukinumab.
Psoriasis. Remember those Th17 cells? The riot police? Block their main weapon, IL-17, and the psoriatic plaques on the skin can just melt away. And interestingly, IL-17 is not the warden for TB, so the infection risk is slightly different.
What about IL-6 inhibitors, tocilizumab?
This became famous during the COVID-19 pandemic and also in CAR T-cell therapy. IL-6 is a major driver of the cytokine storm, the overwhelming systemic inflammation that causes fever and shock. Tocilizumab blocks the IL-6 receptor. It cools the patient down without completely shutting off their T cells.
So let's go back to Mrs. G. She has this horrific GVHD. She's on tacrolimus, the calcineurin inhibitor. She's on high-dose steroids, the sledgehammer. And it's still not working. Her gut is still bleeding.
This is what we call steroid refractory GVHD. The mortality rate here is very, very high, so we have to look for other targets. We might try a drug like ruxolitinib.
And what is that?
It's a JAG inhibitor. It works inside the cell to block the signaling that comes from cytokine receptors. It's like putting earplugs on the cell so it can't hear the inflammatory orders from the outside.
Or maybe something like vitalizumab, to stop more T cells from getting into the gut.
We could try. But again, every layer of suppression we add steroids plus tacrolimus plus ruxolitinib dramatically increases the risk that a simple mold spore that she breathes in will now be able to kill her.
It's a daily, hourly negotiation between rejection and infection.
It is. And for Mrs. G, we just have to hope we can dampen the graft's attack enough to let her gut heal before a fungus or a virus finds her in this weakened state.
Wow. We have covered a massive amount of ground. From the molecular Velcro of rolling leukocytes all the way to the nuclear codes of T-cell activation.
We've really charted the course of immunopharmacology. We've moved from the era of kill everything, like with chemotherapy, to suppress all inflammation, like with steroids.
To now intercept the specific message with the biologics.
Exactly.
Where are we going next? What does the future look like?
The future, I think, is living drugs. We mentioned CAR T cells, which are T cells that we engineer to kill cancer. But imagine the opposite. Imagine engineered tregs.
The regulatory T cells. The peacekeepers.
Yes. Imagine taking T cells from a patient like Mrs. G, taking them to the lab, engineering them to be super potent peacekeepers that are specific only for her gut tissue, and then infusing them back into her.
So instead of a drug that blocks a receptor, you're sending in a living diplomat to actively negotiate a ceasefire.
You're programming the immune system to repair and tolerate, rather than just blocking its ability to destroy. We're blurring the line between pharmacology and cellular engineering.
That is a mind-bending place to stop. Listeners, this was a dense one. If you want to really visualize that Velcro we talked about, the rolling and adhesion, go to Goodman and Gilman, chapter 34, and look at their diagrams of leukocyte extravasation.
They're fantastic.
And then go to Katsung, chapter 55, and look at the drug tables. Specifically, the toxicities. You need to know why tacrolimus hurts the kidneys. It's all there.
The deep dive provides the map, the text provides the territory. You still have to read the chapters.
Thanks for listening. Stay healthy and stay curious.
And wash your hands. Your skin barrier is your best friend.